First of all, I want to express my gratitude to the organizers of this conference for their kind invitation to participate in this conference and deliver a lecture. So, the title of my talk is Initial Boundary Value Problems for the Higher Order Nonlinear Schrodinger Equation. And I want to start with the origin. What is this equation? So, the nonlinear Schrodinger equation in one special dimension is well known and is written in such a way. Here, U is a complex valued function. P, alpha, and lambda are real non-zero constants, and P is positive. And besides this equation, there is another famous equation, such as the Korteweg-de Vries equation, which is written in the following form. Here U is a real valued function, and B and beta are real constants. Beta is not non-zero. And besides the Korteweg-de Vries equation, one can consider its generalizations where, with more general nonlinearity, for example, the so-called modified Korteweg-de Vries equation, or more general K generalized Korteweg-de Vries equation. So we have two different equations, and from the first sight they have nothing in common. However, certain mathematical properties are similar. For example, for these equations, if we consider the initial value problem, then the norm is L2 is preserved. For the nonlinear Schrodinger equation, it is proved in the following way. Of course, we consider a good solution, which is smooth and vanishes at infinity. And if one multiplies this equation by 2u bar, where this is a complex conjugate operation, take the imaginary part and integrate, then after very simple calculations, one can derive this conservation law. But for the KdV equation and for its generalized KdV equation, the conservation law is the same. And it's also proved by the same method. Here U is not his real valued function, it is not complex. Then simply let's multiply our equation by 2u, integrate, and then after simple integration, we again obtain this conservation law. So these properties are the same. Next. So besides the conservation law in L2, there are also the conservation laws which are referred to as energies. For example, for the nonlinear Schrodinger, this quantity is preserved, and for the generalized Korteweg-de Vries equation, or in particular for the Korteweg-de Vries equation itself, this quantity is also constant. So these properties are similar for these two different equations. Besides that, if we consider the corresponding linearized equation, which can be written in such a form as a linear Schrodinger equation, this linearized Korteweg-de Vries equation, which is also called the Airy equation, then it's the solution of the initial value problem can be easily found by the Fourier transform, and in all of these two cases, it can be written in such a form, and what is important, that this polynomial is real, and such equations are called dispersive equations. There are also some other common properties. For example, the well-known inverse scattering transform method can be applied for the nonlinear Schrodinger equation and for Korteweg-de Vries equation, but I don't use this method in my investigation, so I don't want to speak about it. So, now the natural question is, the natural step is to combine these two equations. And let us consider the following one, which includes the terms from the nonlinear Schrodinger equations and from the Korteweg-de Vries and the generalized Korteweg-de Vries equation. And consider the following equation. Here U is a complex valued function, and these parameters are real constants. And this equation is called the higher order nonlinear Schrodinger equation. And this is the equation I want to speak about. So, for me, as a mathematician, it's enough that we have an equation, so it is to study to now we have to investigate it. Maybe it's not a perfect approach, but as a bonus, I want to say that this equation also has physical meaning. There are some wave processes, they are described by this higher order nonlinear Schrodinger equation. This was sent, such articles were sent to me by my co-authors. I will speak of them later. However, trust me that such equation is also used in physics, in a real physical situation. And now let's study the properties of this equation. Here you see that nonlinearity is written in such a form. It also includes, in general, it also includes this term which is non-divergent. But even in this situation, the L2 norm is also conserved. And it is proved by the same method. These simple calculations show that if we multiply our equation by 2u bar, take the imaginary part and integrate, then again, as for the nonlinear Schrodinger equation itself and the Korteweg-de Vries equation, again this norm is conserved. And of course, this nonlinear equation is also the dispersive equation. If one throws away the nonlinearity, then it consists of the terms which are from the linear equation, from linear Schrodinger equation, from the area equation, and so it's also the dispersive equation. However, this is all in general. For example, let us try to find the analog of the next conservation law of energy. We know that such quantities are conserved for nonlinear Schrodinger equation and the KdV equation. But what is here? And here we have the following equality. And so we have here such a term. And of course, if we want that this integral, or this quantity in brackets, is conserved, then this term must be equal to 0. And of course, when it is so? For example, either the coefficient gamma is 0 or the parameter p is equal to 2. Because if so, then this, if here p is equal to 2, then this integral is also equal to 0. So only in this situation. In another situation we have, it's a bad term. And another obstacle in the study of such an equation is that in this equation we have a term modulus of u in the degree p. And if p is equal to 2, it is a very good function. It is smooth function with respect to u. But if not, then it is, if for example p is less than 2, then it is a bad function in the zero, yes, in the zero. So, since the case p, where p is equal to 2, it was the situation when the investigation of such an equation was begun. And if p is equal to 2, and if we compare it with the KdV equation, this case corresponds to the so-called modified KdV equations, not to the Korteweg-de Vries equation itself, but to the modified one. And in the case p equals to 2, then the high-order nonlinear Schrodinger equation is written in such a form. And what are the previous results? In 1997, in the paper by the French mathematician Camille Leray, there was constructed a theory of the initial value problem, and such results were established. For example, if U0 is from L2, there exists a solution which preserves this L2 norm and has some additional smoothness. I will speak about this later. Then, if U0 is from H1, then a class of correctness, well-posedness was constructed. And these results they corresponded to the ones established previously for the KdV and the modified KdV equations. Then later, in certain papers, the local well-posedness results were established for in less regular case. In this case, HS not less than 1/4. And it's all. For other values of p, there were no results. And for example, there were no results in the case p equal to 1. And this case corresponds to the KdV, to the Korteweg-de Vries equation itself. And the idea of the first part of my study is to consider the case when the nonlinearity has the quadratic degree. So I have to restrict myself to the case where the coefficient gamma is equal to 0, so the non-divergent term is absent. And the crucial idea of the study is to study the solutions in weighted L2 spaces, weighted at plus infinity. And it depends upon the sign, this sign. If we have here not plus then minus, then it will be weights at minus infinity. So let's introduce the following notation. It's not canonical, but for me it is convenient. So we have L2 sigma. What is it? So we have this property. So we have additional weight at plus infinity. And what is the result? Start with the result. If U0 is from L2 3/4, then for any t capital, there exists a unique solution to this problem from this space. CW means weak continuity. And here my study uses the ideas of this corresponding investigation of the Korteweg-de Vries equation, which was done by me and my scientific guy Stanislav Nikolaevich Krushkov in 1983, and this peculiar, maybe peculiar number 3/4 also appeared, and for the Korteweg-de Vries equation, the same result was obtained. It is this result is not optimal. And next, for example, in the papers by Jean Bourgain, this weight was thrown away, and by Jean Bourgain proved that the initial value problem for the Korteweg-de Vries equation is globally well posed only if U naught in L2 is in L2. Moreover, after him, such a result was obtained for U naught from negative Sobolev space. However, these results are based on the use of the so-called Bourgain spaces, and this study used very sophisticated harmonic analysis. And for example, it's very important that our nonlinearity has the following form, and in particular, nobody knows if one can substitute here U squared by, for example, some function which only has the same growth rate. And nobody knows how to use the Bourgain spaces in our case, when we have here modulus of U. Modulus of U, U. So it's an open problem. So I don't know how to apply Bourgain spaces for my equation. Maybe in the future. The ideas of Khrushchev and my were so that this functions, the space of functions when we established well-possedness is very simple. It does not require any smoothness, only L2 with the weight. And although these ideas now looks like rough and archaic in comparison with the Bourgain methods, these ideas, it turned out that these ideas can work here, and the same result can be established. Again, what I want to say, what conservation laws or global a priori estimates are used here. The first one is, of course, the conservation law is L2, but the next one is the so-called smoothing effect. Let's multiply the equation not by 2u bar, but 2u bar and the auxiliary function psi, which is smooth, non-negative, and non-decreasing. And again, take the imaginary part and integrate, and then the following equality is derived. And I want to attract your attention to this term, the second term, and if psi prime is non-negative and is positive on, for example, a compact interval, then we have additional term which has good sign. And in particular, the following estimate, which is called the local smoothing effect, can be obtained. And in fact, the result on existence is valid only if U naught is from L2. But if we want to establish uniqueness, then the idea is the following. The idea is to invert the linear part of the equation and to use the fundamental solution of this linear operator. And then one can obtain the following integral representation of our solution. And here we do not have to differentiate nonlinearity. Here we differentiate the kernel. And just the properties of the kernel of this fundamental operator, the fundamental solution of the operator, they lead to that peculiar number 3/4. for the Korteweg-de Vries equation, when we with Khrushchev established these results, we used the well-known properties of the fundamental solution of the area operator, and it's expressed through the area function. And here I had to study the properties of the fundamental solution of the operator corresponding to my higher order Schrodinger equation. Next, besides the results on global well-possedness, I have established some results on large time decay. Such results are popular for the dispersive equation. In fact, since we have the conservation law in L2, the results on large time decay in L2 are impossible for our equation itself. But we have to supplement our equation with certain damping. If the function a is of strictly positive on the whole line, then the result is obvious. But here the idea that it is non-negative and strictly positive only at infinity. So this case is called the case of localized damping. So the theorem here is the following. So if a function a is from L infinity, is non-negative and is strictly positive at infinity, then if u0 is from L2 3/4, and then for the unique global solution, the following estimate is valid. So we have exponential decay of the L2 norm. And the proof exploits certain contradiction argument, and these constants, mu and c, cannot be evaluated explicitly. So this is the situation, such a situation with the nonlinear higher order Schrodinger equation on the whole line for the initial value problem. And the next item of my talk is devoted to the problem on the bounded interval, or the initial boundary value problem. So again, consider the higher order nonlinear Schrodinger equation on the bounded interval I capital. Here, besides the initial condition, we set such boundary conditions. So we have here one boundary condition on the left side and two boundary conditions on the right side, and it again originates from the sign of this term. If I replace here plus by minus, then we must also change the situation and set up this extra condition also on the left side. But in this situation, this is the such conditions are set. Here again, u is a complex valued function. The function a is real valued. It is non-negative, and it is positive on a subset of our interval I capital. This is a condition A capital. So this subset omega can be very small, but it is not empty. And so we have the situation where the damping is effective only locally. Previously such a problem was studied in other papers, and but only in the case when p is equal to 2, the simple case, and where the nonlinearity has no derivatives. So for such an equation. And again, it was as similar to the result for the initial value problem I told a few minutes ago. The following result on large time decay was established. In our study, we consider not only the case p equal to 2, but in general form, and we consider the case when a nonlinearity also contains derivatives. So Here, the result. In order to describe the results, let's introduce the following functional spaces for the initial function. X capital 0 is simply L2, then X capital 3 is the following space. It takes into account boundary conditions, and for intermediate values of S, it is obtained with the use of interpolation. And for our solutions, we use the following space. It preserves this space x3 with respect to t, and also has additional smoothness. And in the case S equal to 0, we also use the weaker space. Here, continuity is only weak. And the first theorem is the theorem on global existence of weak solutions. If U0 is from L2, A is from L infinite. Now, for these results, this damping term can be absent. And either P is from this interval, or if gamma is equal to 0, then from this interval can be enlarged. Then for any T capital, there exists a solution from this space. So, this restriction is P less than 3 is the penalty for this for existence of this non-divergent term. And the first conservation law, the first a priori estimate, not of course conservation law, is again obtained by the same idea. Let's multiply the equation by 2u bar, take the imaginary part and integrate, then we have the following equality. And of course, the following estimate can be derived. The next global a priori estimate is as in the case of the initial value problem, is obtained with the use of the multiplication of the equation not only by 2u bar, but with the following auxiliary factor, and here it can be chosen as simple form or simply x, and then after if we consider the third derivative, then after simple calculations, it is transformed to the following term, which is good, and it is used to obtain extra global a priori estimate. Next, if P is not greater than 2, then global well-posedness in the weak class can be obtained. Here's the following result. Next, we also need certain results of global well-posedness in more regular classes. And if U0 is from X3, that is from H3 with corresponding compatibility conditions on the ends of the interval, P is equal to 2, then the problem is globally well posed in such a space. If P is not equal to 2 but can be less than 2, then and this the function modulus of u in the degree p is not a smooth function, then we have only the result on existence and uniqueness without continuous dependence. But it is sufficient for our next purposes. What is interesting to note that we have, as a corollary, we have the following result on internal regularity. If U0 is from L2, then we can consider the corresponding solution from this space. What is this space? Y capital 1T capital. So here we have L2 on the interval 0T, and here we have H1, H2, and oh no, here's a mistake, misprint. Of course, Y0, and here we have H1, of course. Then, for every epsilon, there exists T0 from the interval 0 epsilon, that the function of such a function lies in the space H1, 0, and it is our space X1. And application of the preceding theorem in the case S1 S equal to 1 gives us the following corollary. So we have additional smoothness. And then the scheme of the next investigation is in fact now at this moment is in fact traditional, and it's not our idea. Our task was only to apply this scheme to our concrete equation. So, what is used here? What is the scheme of the proof? Let omega is an arbitrary interval from our inside our interval I capital, and let us choose the following function psi. It's not very simple, but it exists, such a function exists, and then it is not our results, but the result by Capistrano, Filio, Poisotto, and Rosier for the Korteweg-de Vries equation itself. And if one considers the initial boundary value problem for the linearized Korteweg-de Vries equation, non-homogeneous, then the following Karleman type estimate can be obtained. I want to attract your attention that in the left side of this inequality we have an integral over the whole rectangle. And here is the integral not only, not over the whole rectangle, but on the sub-rectangle. Here is not I capital, but omega. And with the use of this Karleman type estimate, the following unique continuation property can be obtained. What is this property? If we have the solution which is 0 on the sub-rectangle, then it is 0 on the whole rectangle. And the idea of the proof is to consider the solution of our nonlinear high-order Schrodinger equation as a solution of the linearized homogeneous Korteweg-de Vries equation. So we move all other terms to the right side of the equation, and our corollary provides that this right-hand side has the corresponding smoothness. And then, after that, the right-hand side can be estimated by such a term, and after that, the Karleman type estimate ensures that we have the following inequality. And of course, if our solution is 0 for x from omega, so here we have 0, so then we have 0 in the left hand side, so our solution is 0 on the whole rectangle. And after that, the following, after with the use of this unique continuation principle, the following Holmgren type inequality can be obtained, and this proof is performed with the use of contradiction. Here again, this constant C cannot be evaluated explicitly, And what is the main feature of this estimate? Here, in the left-hand side, we have the integral over the whole rectangle. Here also, but with the function a, and function a is non-zero only on sub-rectangle. Okay, so this is the last exertion. Thank you very much for your note. So this is the final result, and I want to say that this result was obtained with a collaboration with some mathematicians from Latin America, and it's published in the previous year. Thank you for your attention. Thank you.